Hi, I'm a fourth year graduate student under Professor Irina Mitrea at Temple University. My research interests are geometric measure theory, harmonic analysis, and partial differential equations. What I'm going to speak today is about Rellich type identities and their role in the treatment of elliptic boundary value problems in Lipschitz domains. Let me first talk about the motivation. The LP Neumann problem in the domain omega in Rn for p strictly between 1 and infinity has these conditions. U is of class C2 in the domain omega. This is to ensure that we take the Laplacian of U. And the Laplacian of U is equal to 0 in the domain. The non-tangential maximum operator of the gradient of U is in LP on the boundary. The normal derivative of U is equal to given LP data F. Here, nu is the odd-ordered unit normal vector on the boundary. And for the capital X on the boundary and a fixed number kappa, which is bigger than 1, the gamma of X is defined by this. The point Y in the domain such that the distance from the vertex X is less than kappa times distance from the boundary. So the point cannot be close to the boundary without being close to the vertex X. If the domain omega is the upper space, then this gamma of X is going to be an unright straight cone at vertex X of aperture kappa. In general, this is called the non-tangential region. The non-tangential maximum operator of U at X is defined by the supremum of absolute value of U in this non-tangential region. The non-tangential trace of V at X is defined by the limit of V when Y goes to X along this non-tangential region. And in this equation, the non-tangential, the normal derivative of U is defined in the non-tangential sense, which is the inner product between the non-tangential trace of the gradient of U and the outer unit normal vector nu. And here, the second condition is called the PD condition, and third condition is called the size condition, and the last condition is called the boundary condition. And the idea is that we reduce matters to solving a boundary integral equation. So we seek a solution of the Neumann problem as U is equal to the operator of S of G, where the operator S of G at X is defined by the integral over the boundary of the function capital E of X minus Y times U of Y, the sigma of Y, where the function G is defined on the boundary into R, and the point capital X is in the domain, and capital E is the canonical fundamental solution of Laplacian in Rn, which means the Laplacian of E is equal to delta distribution. And this operator S is called the boundary to domain single layer potential operator. This is because the function G is defined on the boundary. If we take the single layer, this is going to be defined in the domain. Let me introduce some observations about the single layer potential operator. Single layer satisfies the PD condition, which means the single layer of G is harmonic in the domain omega. This is because if you look at the definition, and if we take the Laplacian with respect to X, then by the dominated convergence theorem, we can move the Laplacian to the inside of the integration. Then this is going to be a delta distribution at X. But Y is never going to be X because Y is on the boundary and X is in the domain. So this is going to be 0. That's why the single layer of G is a harmonic function in the domain omega. And it satisfies the size condition, which means the non-tangential maximum operator of the gradient of single layer of G is in LP on the boundary whenever G is in LP on the boundary. This is due to the Calderón-Zygmund theory. And from the Calderón-Zygmund theory again, for the boundary condition, we have the jump formula, which is the non-tangential trace of the normal derivative of single layer is equal to negative 1f I plus k star sigma almost everywhere on the boundary. Here, I is the identity operator, and k star is defined by the limit of truncated integral operator. And it pretty much looks like the double layer potential operator. But here we are taking the normal derivative with respect to X. But for the double layer, we take the normal derivative with respect to Y. So K star is the formal adjoint operator of the double layer potential operator. So the only remaining thing is for the Neumann problem is the boundary condition, which is the non-tangential trace of the normal derivative is equal to the given LP data F. So the solving the Neumann problem is reduced to finding the function g such that -1f identity plus k star of g is equal to the given LP data F. And if we invert this operator, then the solution is going to be -1f I plus k star inverse F. So we need to invert this operator to solve the Neumann problem. Let me talk about the history briefly. If omega is bounded and C1, then K star is compact on LP on the boundary for any P strictly between 1 and infinity. This has been proved by Fabs, Yodite, Riviere in late 1970s. And we know that -1f I is invertible operator, which means this operator is Fredholm operator of index 0. And if K star is compact, so if we add the compact operator, this is going to be again the Fredholm operator of index 0, which helps us to invert this operator because invertibility is equivalent to injectivity or surjectivity. But if omega is less smooth, let's say omega is Lipschitz but not C1, then K star is no longer compact. So the Fredholm operator theory is not applicable in that case. In 1984, Vercola were able to prove that if omega is Lipschitz, then -1f I plus k star is invertible on L2 on the boundary, even if k star is not compact. In 1987, Dalberg and Koenig has proved that if omega is bounded and Lipschitz, then -1f I plus k star is invertible on LP on the boundary for P between 1 and 2 plus epsilon, where epsilon is depending on the Lipschitz constant of omega. And the range of P here is optimal in the sense of that if P is strictly bigger than 2, then we can construct the Lipschitz domain for which the invertibility fails. Our goal for today's talk is prove that -1f I plus k star is invertible on L2 on the boundary, which is based on the Vercola's result. Let me start to talk about the Rellich identities. Let the function u be a function defined from the domain omega into R, such that u is of class C2 in the domain omega, and u is harmonic in the domain. And the non-tangential trace of the gradient of u exists. The non-tangential maximum operator of the gradient of u is square integral function on the boundary. I will say this condition as star. And the normal derivative of u was defined by the inner product between the non-tangential trace of the gradient and the other union normal vector nu. And we define the tangential gradient as the non-tangential trace of the gradient of u minus the normal component. Then these are the square integral functions on the boundary. This is because, first of all, the non-tangential trace is controlled by the normal non-tangential maximum operator, but the non-tangential maximum operator from the condition star is square integral function on the boundary. That's why these are the square integral functions on the boundary. And the tangential gradient is perpendicular to the normal vector. So in this section, we are going to establish the Rellich identity, and then we're going to prove the equivalence between the normal derivative and the tangential gradient in A2 on the boundary. To establish the Rellich identity, for a fixed vector E in Rn, we define the vector field F by this. Then F has some properties. First of all, F is smooth vector field in the domain. This is because U is harmonic, which implies that U is an analytic function in the domain omega. That's why the vector field F is going to be smooth. And thus F is L1 locally in the domain omega. So we can take the divergence in the sense of distribution. And the non-tangential trace of F exists because from the condition star, the non-tangential trace of the gradient of U exists. And then if we take the non-tangential trace to the F, everything exists. Moreover, the non-tangential trace of f is at 1 on the boundary. This is because from the condition star, the non-tangential maximum operator of the gradient of u is square integral functions on the function on the boundary. And non-tangential trace is controlled by the non-tangential maximum operator. For the first term, we have the square of the gradient of u. So if you take the non-tangential trace, this is going to be square at 1 on the boundary. And for the second term, we have the gradient of u twice, which implies that the second term is the non-tangential trace of second term is at 1 on the boundary. That's why the non-tangential trace of f is at 1 on the boundary. And f is divergence-free vector field. Let me prove the divergence-free part rigorously. From the definition, divergence of f is the summation from 1 to n of partial j of fj. And if you take the partial j to the first term, we have this first term in this line. And for the second term, we take the partial j first to the partial j of u. Then we have the partial j square of u, which gives us the second term here. And finally, we take the partial j to the gradient of u, which gives us the last term in this line. And if you look at the first term and last term, if you change the ordering of the summation, they're going to be canceled out each other. And for the second term, the inner product does not depend on the summation, so we can pull out. Then we have the summation of the partial j square of u, which is the Laplacian of u. But from the condition star, u was the harmonic function, so this is going to be 0. That's why the f is divergence-free vector field. And we apply the divergence-free of non-tangential version to f. Then we have integral over the domain of divergence f. Dx is equal to integral over the boundary of mu dot non-tangential trace of f, the sigma of x. But f was divergence-free, so this is going to be 0. And from the definition of f, the non-tangential trace of f was this integrand minus this integrand times 2. And then from this identity, we have this identity. So I would say this as left-hand side and this as right-hand side. And E10 is perpendicular to the normal vector, where E10 is denoted by this. But then the square of the non-tangential trace of the gradient of u is the inner product of itself. Then we can decompose the non-tangential trace of the gradient into the tangential gradient and the normal component by this. And by the orthogonality of tangential gradient to the normal vector, we have square of the tangential gradient plus square of the normal derivative. And if you plug in this equation to the left-hand side, then we get this. Moreover, for the right-hand side, we can decompose this gradient of u into the tangential gradient and the normal component. Then we have this. For the first term, E10 was originally just E, but by the orthogonality of tangential gradient of u to the normal vector, we can replace by E10. And left-hand side was equal to right-hand side, so this second term can be observed to the right-hand side. Then we get this identity, which is called the Rellich identity. And then our next goal is to prove the equivalence between the tangential gradient of u and the normal derivative of u in A2 on the boundary. Let omega be a special Lipschitz domain, which means omega is the upper graph of some Lipschitz function phi. Then by Raja-Marshall's theorem, phi is differentiable almost everywhere in Rn-1. And by Lipschitzianity, L infinity norm of the gradient of phi is bounded by some constant capital M. And if capital X is on the boundary, then capital X is little x prime and phi of x prime, because omega is the upper graph of the Lipschitz function phi. Then the outward union normal vector nu at point capital X on the boundary is going to be the gradient of phi x prime and -1 over the magnitude. This is because if you look at the point, the tangential direction is this. So that's why the normal derivative has this form. a normal vector has this form. And if you select the vector E as negative En, which is the negative nth standard unit vector, then the inner product between E and nu is going to be the product of the nth component, which is this. And the denominator is greater than or equal to 1. So this is going to be less than or equal to 1. And by the second item here, this is going to be greater than or equal to 1 over square root of 1 plus m squared. So we have like transversality to the boundary of omega. And the inner product between E and nu is comparable to the constant. So far we had the Rellich identity here. And to prove the equivalence between the tangential component of u and the normal derivative of u in L2, I will start from the L2 norm of the tangential gradient of u. Then by the comparability of constant of the inner product between E and nu, we can bound by this. And then by the Rellich identity here, we have this. Moreover, by the Cauchy-Schwarz inequality, we have this. This is because E10 and the inner product between E and nu are bounded by the constant. And we know that for AB is less than or equal to a square, epsilon times a square plus b square over epsilon. If you apply this inequality to this, then we get this. So we can make the tangential gradient part to the small number and the normal derivative part to the large number. And if c times epsilon is less than 1, then this can be observed to the left-hand side here. So if we choose the c epsilon such that epsilon is less than 1/2, then we obtain this inequality. And for the reverse inequality, if we start with the L2 norm of the normal derivative of u, and by Rellich identity, we have the reverse inequality. So under the hypothesis star, we have equivalence between the tangential gradient of u and the normal derivative of u in L2 on the boundary. Now we return to the Neumann problem. Let omega plus be the inside of the domain omega and omega minus be the outside of the domain omega, and u be the singularity of g for the square integral function g. Then you satisfy the smoothness in omega plus or minus, and u is harmonic in omega plus or minus. And non-tangential maximum operator of the gradient of u is in L2 on the boundary. And we had a jump formula from the Calderón-Zygmund theory, which is the non-tangential trace of the gradient of u on the boundary of omega plus or minus is equal to minus or plus 1/2 identity plus k star of g almost everywhere on the boundary. And the important thing is tangential gradient of the single layer of g does not jump, which means the tangential gradient of the single layer of g is equal to on the boundary of omega plus is equal to the tangential gradient of single layer of g on the boundary of omega minus. And from the Rellich estimate, the non-tangential trace of the boundary of omega plus of the normal derivative of single layer of g in L2 is equivalent to the non-tangential trace of the tangential gradient on the boundary of omega plus. And the tangential gradient does not jump. So this is equal to this or on the boundary of omega minus. And again, by the Rellich estimate, this is equivalent to the normal derivative, non-tangential trace of the normal derivative of single layer of g on the boundary of omega minus in L2. So consequently, this is going to be equivalent to this. And from the jump formula, we have the equivalence in L2 space of these operators. So we have these operators, equivalence of these operators in L2 on the boundary. And we can express G as 1/2 I plus k star of G minus negative 1/2 I plus k star G. Then by Minkowski inequality, L2 norm of these is less than or equal to the summation of L2 norm of these operators. And by this equivalence here in L2 space, the L2 norm of G is bounded by some constant c times the L2 norm of plus or minus 1/2 identity plus K star of G. So the L2 norm of the plus or minus 1/2 identity plus K star of G is bounded below by L2 norm of G. So on L2 space, on the boundary, plus or minus 1/2 I plus K star is an injective semi-Fredholm operator if omega is a special Lipschitz domain from this inequality. And more complicated version of Rellich identities, we have lambda I plus K star is also an injective semi-Fredholm operator if absolute value of lambda is greater than 1/2. And functional analysis theory gives us plus or minus 1/2 I plus K star is an injective semi-Fredholm operator of index 0, and hence it's invertible. This is because, first of all, if lambda is sufficiently large, then we can apply the Neumann series, which gives us the invertibility of lambda I plus K star for sufficiently large lambda. And from the large lambda to the end point, which is plus or minus 1/2, we can find the continuous path between 2 points. And on this path, they have the same index. But for the large lambda, it's invertible, which means the index is 0. And on the continuous path, if you return to the end point, these operators have the index 0. And it gives us the invertibility. And we can solve the Neumann problem on L2 on the boundary if omega is special Lipschitz domain. Thank you for watching this video. And if you have any questions, please send me an email here. Thank you.